So the additional properties that we mentioned for Rn relative to the dot product also hold for general inner product spaces. For instance, a generalized version of the Cauchy-Schwartz inequality can be obtained for a general inner product space. And this inequality is stated as follows. Supposing that V has an inner product, so it's an inner product space. So given two vectors x and y, then the absolute value of the inner product of x and y will not exceed the product of the lengths of the vectors x and y. To see why this inequality holds, let's consider the function given by f of x equals the magnitude of x minus xy squared. So here x is an arbitrary real number, and vectors x and y are fixed. Okay, so given x and y. So we can view this as a function on R. So note that f of x is a non-negative function. So it takes non-negative values for any real number x because we are taking the magnitude, square of the magnitude of some vector in V. And the magnitude is, or the length is non-negative. Moreover, by definition of the length, we can write f of x as follows. Okay, the square of the length of x minus xy is the inner product of vector x minus xy with itself. So applying the properties of an inner product, one of the four properties, this inner product equals the inner product of x, vector x with itself, that is the square of the length of x plus the inner product of x minus scalar x times vector y. So that's equal to negative scalar x times the inner product of vector x and vector y. The same value is obtained when you take the inner product of negative xy with x. Okay, so those two inner products give this middle term, negative 2 times inner product xy times scalar x. Finally, the last term is obtained by taking the inner product of negative xy with negative xy. So that's equal to x squared times the square of the magnitude of y. So this computation shows that f is a non-negative function, non-negative real valid function, which is quadratic. Okay, a quadratic function with coefficients magnitude of y squared, negative 2 times the inner product of xy, and the square of magnitude of x. So this is a quadratic function whose graph is a parabola that opens upwards because the leading or the coefficient of the quadratic term is positive. Technically non-negative, but let's assume for simplicity that y is a non-zero vector. Okay, so its graph is a parabola that opens upwards. And recall that if you have a quadratic function of this form, whose graph is a parabola that opens upwards, then the vertex, which is the lowest point on the graph, has coordinates given by this in terms of the coefficients of the quadratic function. Okay, so in our case above, a is equal to the square of the magnitude of y, b equals 2 times the inner product of xy, and c equals the square of the magnitude of x. Okay, so because f is a parabola that opens upwards and non-negative, so this tells us that the roots, or rather the parabola, does not cross the x-axis, or it can cross the x-axis at the vertex. Okay, so that's equivalent to saying that the discriminant of the quadratic function is negative or 0. Okay, so the negative, or rather the discriminant is given by b squared minus 4ac. Our b, as we mentioned, is given by this quantity. Our a is given by this quantity. C is given by this quantity. So this is the discriminant. Okay. So this difference is less than or equal to 0. That's equivalent to saying that 4 times the square of the inner product of xy is less than or equal to 4 times the square of the length of x times the square of the length of y. The conclusion follows by taking the square root of both sides. So that's how we get the Cauchy-Schwartz inequality. An important application of the Cauchy-Schwartz inequality is the triangle inequality. Okay, so we are familiar with the triangle inequality for real numbers, so with respect to the absolute value. So in fact, an analog of that inequality can be obtained for vector spaces with a well-defined inner product or well-defined length. These quantities here are lengths of vectors. So for any vector xy in an inner product space V, okay, the length of the sum, the vector sum x plus y, will not exceed the sum of the lengths of x and y. Okay, so that's so in R2, we can imagine this by the parallelogram law in adding two vectors. So this is vector y, this is vector x. So the sum is the vector whose initial point is the initial point of y, terminal point is the terminal point of x. Okay, and the length of this yellow vector is clearly less than the sum of the length of this vector with the length of this vector. So we can actually derive this immediately from the Cauchy-Schwartz inequality by recalling that the length of a vector in an inner product space is defined in terms of the inner product. Okay, so the inner product, rather the length of x plus y is the square root of the inner product of x plus y with itself. Or equivalently, the length of x plus y squared equals this inner product. And we can write this inner product as this expression. Again, by applying properties of the inner product. This quantity is equal to x inner product with x. That's this quantity here, plus inner product of x with y, plus inner product of y plus x. Those two are equal. You add them and obtain this middle term. And finally, the last term is obtained by taking the inner product of y with y here. That's the square of the magnitude of y. Okay. By the Cauchy-Schwartz inequality, this inner product in absolute value is less than or equal to 2 times the magnitude of x times the magnitude of y. So this is less than or equal to the square of the magnitude of x plus magnitude of y. And the triangle inequality is obtained by taking the square root of both sides. We can do that because the expressions involved are non-negative numbers. Okay. So given vectors x and y in an inner product space V, the proof of the Cauchy-Schwartz inequality implies that the function that we used, this quadratic function, will be least when f of x is the vertex of the graph of the function. Recall that we mentioned that the graph of this is a parabola that opens upward. So the minimum value for f of x is obtained at the vertex. And we have a formula for the vertex, no? So rather the coordinates of the vertex. The x-coordinate of the vertex is given by the inner product of xy with or divided by the square of the length of y. And this is equal to the quotient of the inner product of xy by the inner product of y by itself. So this is the x-coordinate of the vertex, and the y-coordinate of the vertex, which is the smallest value for this quantity, is given by this expression. Note that the function f of x is equal to the square of the distance between vector x and scalar multiple of y by x. So in other words, f measures the distance of vector x from scalar multiples of y. But scalar multiples of y are the vectors that lie on the span of y. So these preceding remarks tell us that among the vectors in the span of y, the closest vector to x is given by xy with x equal to this quantity, inner product of xy over the inner product of y. If V is two-dimensional, we can draw the situation. So here it is the picture when V has dimension 2. In this case, the span of y is the line determined by vector y. Okay, so we take all vectors lying along that line, and we measure the distance of each vector from vector x. So the remark tells us that among those vectors, which are scalar multiples of y, the one that has the minimum distance from x is given by this yellow vector, given by inner product of xy over inner product yy times vector y. Okay, and the distance between x and that vector is equal to the magnitude of this vector, which is the difference of x, or rather the difference of this yellow vector from x. You can verify that this vector x is perpendicular to y, or equivalently, it's perpendicular to the line determined by y. So the inner product is 0. And so this observation gives us the idea that the most natural way of defining the projection of a vector x on y in an inner product space is through this vector, the scalar multiple of y by inner product of xy divided by inner product of yy. For instance, even if we cannot draw vectors in V in this vector space, Then with this inner product, we can compute vector projections. So here. So for instance, if we consider f and g to be the constant function 1 and linear function x respectively, then the projection of f on g by the formula is equal to the inner product of f and g divided by the inner product of g and g. So this is a scalar, then multiply that to g. Okay. But these inner products are computed again using this definition for our inner product as shown. Okay, so we see that the inner product of f and g is 1/2. The inner product of g and g is 1/3. Okay, so we see that the projection of f on g is equal to 3/2x.